All right. In this section, we're going to begin 11.8, power series. This is when we start applying our knowledge of series. All of our previous sections, building up our knowledge of series, it's all kind of building towards these last three sections where we start turning series into functions and using them to do some calculus like integration and derivatives, things like that. Okay, so let's talk about the transition from series into functions. Okay, so in all our previous sections of chapter 11, we had a series like this, the sum from 1 to infinity of a sub n, where all of these are real numbers. Okay, I've represented them here as these ANs, but these ANs are real numbers, right? So there's no independent variable in here. There's no x's in this series, right? There's nothing unknown about this series as far as inputs, right? There's maybe the question, and you could ask yourself, does this series converge or diverge? But if it does converge, it only converges to one number, right? It's like I can't play with the inputs of this series to get different numbers out for my sum. So we don't have this structure to plug in different inputs and get different outputs. There's, for one series, there's only one output. Uh, there's only one possible sum if the sum even exists. So when that series converges, it only converges to one number. But maybe we want to make some sort of function out of these series. Maybe we want to introduce an independent variable, an x, and turn these series into functions, okay? This is what this section 11.8 is about. It's about power series, okay? So we're not just going to do this willy-nilly. When we introduce this x, we do it in a special form, okay? So a power series is a series of this form, okay? So I have the sum from 0 to infinity, c sub n times x minus a to the power n. So I have this thing here. So let's dissect this a little bit. First of all, the series is starting at 0. We're used to series starting at 1, okay? Right? We're used to this. It makes absolutely no difference starting at 0. Don't get hung up on that at all, okay? That, it's just a style thing. For some reason in this section, they have this series, a lot of the series starting at 0. It has absolutely no deeper meaning, okay? And now let's continue dissecting this. What are these CNs? Well, these CNs are going to be real numbers, and we're going to call those CNs the coefficients of our power series, okay? So all power series have this form, right? So the only thing that makes one power series different from another are these coefficients and this number here, okay? Like the general structure is always the same. Okay? So these CNs are going to be what makes one power series different from another, as well as this A. What is this A? This A is where our power series is centered, and I'm going to explain what that means in a little bit. But this number A is also a real number. Okay. And these CNs and this A are fixed. If I have a particular power series, these CNs and this A are fixed, and then this X is my independent variable. I can plug in different values for that X. Now, just like with our previous series, series like AN, we have some questions we want answers to. We have these questions like, does the power series converge? And if it converges, what is it converging to? Okay. And we're going to start answering these questions in the series. We're mostly going to talk about the first question, does the series converge? Okay. In later sections, we'll talk about what they converge to. And we're going to see that the convergence of a power series is completely determined by those CNs, okay? Remember, this is my power series. So maybe one power series converges and another doesn't. What determines whether this series converges or not? It's all going to be determined by what coefficients we have, what these numbers are. Okay. For example, let's pick a specific example. Let's say all our CNs are equal to 1. So CN is equal to 1 for all n. And let's say A is equal to 0. Okay. So I'm going to plug those values into this power series. So all my CNs are 1, and this A is equal to 0. Okay, so I have the sum from 0 to infinity of 1 times x minus 0 to the power n. And I can simplify that, right? And it simplifies very neatly as x to the power n. Okay, let's look at this specific power series and ask ourselves, does it converge? And if it converges, like, does it converge for all x? Does it only converge for some x? Does it converge for no x's? So these are the type of questions we're asking. So let's just play around with it. Let's plug in a couple values, okay? So I've listed a couple values here. Let's take it step by step. Okay, so let's say I plug in the value of 1/2 for x, okay? Remember, the series I'm looking at is x to the power n. Okay. So let's plug in 1/2, and when I plug in 1/2, I get this thing, right? I get 1/2 to the power n. Now forget about power series for a second and think about sections, 11.2 through 11.6 or whatever, our first couple sections. What does this look like? Well, that's a geometric series, right? And this would be my R. This value here would be my R, okay? And R is less than 1 in this case. So what does my geometric series test tell me? It tells me that this series converges, okay? So when x equals 1/2, this power series converges. And we could even find the sum, but let's not worry about the sum right now. And does this power series converge for any other x's? Well, let's try plugging in x equals 2/3. Again, plugging into this power series here. Okay, when I plug in x equals 2/3, what do I get? I get this thing, 2/3 to the power n. Again, this is a geometric series and r is less than 1, so this series converges. So there's a lot of values. Maybe you can spot a trend. There's a lot of x values where the series converges. And in fact, we can see our power series is going to converge whenever the absolute value of x is less than 1, right? So I can pick any value of x such that its absolute value is less than 1, and my series is going to converge. And on the other hand, my series is going to diverge when the absolute value of x is greater than or equal to 1. Okay? So let's just dissect before we move on to this text here. Let's dissect this a little bit. Excuse me. There we are. So we had this series x to the n, this power series x to the n. Okay. And we kind of have stated that, okay, this is going to converge when x is less than 1. Okay. So let's say I have this number line. I got 0 right here. And then let's see, -1 here, +1 here. We see that this series converges when x is in this region, right? And it's going to diverge when x is greater than, absolute value of x is greater than or equal to 1. So it starts diverging at -1 and diverges all the way to the left, and it starts diverging at +1 and diverges all the way to the right. But in this interval in the middle, our power series is going to converge. Now, this shows a lot of properties that are kind of in common for all power series. So remember, the power series we started with, this was when all the CNs were equal to 1 and A is equal to 0, right? And what did we see about this particular power series? Well, it converged out at this interval, -1 to 1. Okay, so it converges on interval. And that value 0, the center, is right smack dab in the middle of my interval. Okay, so these are kind of properties that are common for all power series, and we're going to develop that in the next theorem here. But just keep this in mind, keep this example in mind as we state what's going on in the next theorem. Okay, so let's consider a power series. Just some arbitrary power series, c sub n times x minus a to the power n. There are only 3 possibilities. Okay. Possibility 1, the series only converges at x equals a. So let's dissect this a little bit. What are we asking? You know, I have this power series, and what I'm doing is I'm asking, okay, where on the number line does this power series converge? Okay, and let's say I have a. Okay. Let's see what happens when we plug a into our power series. When I plug in a for x, what does my power series become? Okay. My power series, when I plug in x equals a, is just this, I'm adding up 0 an infinite amount of times, which adds up to the number 0. Okay. So when I plug in x equals a, my power series converges. So I can always say that my power series converges at that center, at that value a. Okay. So that's point 1. But maybe our power series converges at more than just a. Okay, and that's what point 2 is going to say. Maybe there's an interval around a where it converges. Okay. So possibility 2 is the series converges on a finite interval centered at a. Okay, so maybe there's an interval around a where the series converges. So maybe it's like it converges at a from a minus r to a plus r. Okay, so maybe our series converges everywhere in here. So let's look at point 2. Let's continue reading point 2. So possibility 2, the series converges on a finite interval centered at a, meaning there's a positive number, capital R, such that the series converges when the absolute value of x minus a is less than r and diverges when x minus a is greater than r. Okay. So think about r as like the distance from a where the series converges. So as long as this distance between x and a is less than r, the series is going to converge. And if that distance is greater than r, then the series is going to diverge. Okay, so we go back up to this example here. We have some number r. If we move r away from a in either direction, our series is still going to converge. But if we move farther than r away, our series is going to diverge. Now, what happens when we're exactly r distance of r away? Okay, so what happens at these endpoints? Does the series converge at these endpoints, or does it diverge? Okay. Well, that's going to be a case-by-case basis. Okay, so we're not going to say anything about it right now, but we're going to have to test those endpoints individually. Okay. Now, let's actually look at interval of convergence first. Okay. So what we've just said is that, okay, our power series always converges at this value a, but maybe it converges on a larger interval as well, from a minus r to a plus r. Okay, so maybe it converges in here. And then we're asking ourselves, okay, what's going on at these endpoints? Maybe our series converges at both endpoints, or maybe just one endpoint, or maybe at neither endpoint. Okay. So we know we're going to have like a finite interval but maybe we're going to include both endpoints, or maybe we're going to include neither endpoint, or maybe we're going to just include one endpoint. Whatever the case may be, whatever we find out, okay, maybe we find out it's this. We call this thing, this interval where our series converges, we call it the interval of convergence. Okay, simple enough. And then there's also this term radius of convergence. Okay, what is radius of convergence? That's just this value r. Think of it as, I have this interval here, and it doesn't matter what's going on at the endpoints. This distance is always the same, right? From the center out, that's always that distance r. So we call that r the radius of convergence. Okay, so let's kind of recap before we move on to the next point. We're saying there's three possibilities for the convergence of a power series. Number one, it's always going to converge at A. It's always going to converge at that value A, okay? So that's possibility one. Maybe it only converges at A. Possibility two, it converges at A plus a finite interval. And we don't know what's going on at the endpoints. Okay, so that's possibility two. Possibility three, the series converges everywhere. Okay, so maybe it converges at A, and it's going to converge everywhere to the left of A and everywhere to the right of A. Okay, so that's possibility number three. Now, I won't prove it, so to speak, but I will give an argument of why these are the only three possibilities. Kind of an informal argument. So let's start with our power series here, C sub n x minus a to the power n. And let's say I'm trying to test if it's convergent or not. And to do that, for whatever reason, I picked the ratio test, and I'm gonna conduct the ratio test on my series. Okay, let's try our ratio test. Okay, so I need to find a n plus 1 over a n. Okay, so we're gonna call this whole thing our a n. Okay, so what's a n plus 1 over a n? That would be this. And let's simplify. And when I simplify, I get the n plus 1th coefficient over the nth coefficient. And then these powers here cancel a lot, and I'm just left with x minus a. Okay. So I conduct the ratio test, and I get this thing. Now remember, the ratio test tells us different things based on what the limit of that is. Okay. So first of all, when x is equal to a, this is going to be 0, right? So a n plus 1 over a n will be 0, and so the limit of 0 is 0, and so my series will be absolutely convergent. Okay, so that's another argument that our power series is always going to be convergent at x equals a. Possibility two. Again, I'm doing ratio test, and I get this thing, and I take the limit of that thing. Okay, and let's say this part, I can find the limit of this part easily. And let's say it's equal to L, and that L could be anything. It could be 4, it could be 100,000, whatever. Okay, let's say that limit exists. Well, then I have a limit here, and then if I choose my x's wisely, I can make sure that the limit of this whole thing is less than 1, right? Let's say this limit's 100,000. I can choose my x's so that this thing is less than or equal to 1 over 100,000. And so then the limit of this overall thing will be less than 1. Right? So as long as these coefficients have a limit, I can choose my x's carefully and make sure that the limit of the ratio test is less than 1, and my series will be convergent for all those x's, right? So that kind of gives me an interval where my series is going to be convergent. My power series is going to be convergent. Possibility three, I'd try my ratio test, and I'm considering the limit of this thing, and I see that the limit, no matter what I do, no matter what x I plug in here, that limit's always less than 1. Well, that would mean my series would be absolutely convergent for all x, meaning my power series would be convergent for all x. Okay? So that's kind of the argument about why these three are the only possibilities. If you don't want to parse that argument, just remember this theorem, okay? That there's only three possibilities for power series. Either it converges only at x equals a, it converges at a finite interval centered at a, or it converges everywhere. Okay. Now, the next thing we want to be able to do is we want to be able to figure out, okay, maybe if I'm given a power series, I want to be able to figure out what the interval and radius of convergence are. Okay, so what's my tool for figuring that out? So let's say we're given the power series c sub n times x minus a to the power n. We're going to be asked to determine the interval and radius of convergence. It's a very common question. So let's talk about how to find the interval of convergence first. So I'm going to take that series, I'm going to take that power series, and I'm going to conduct the ratio test on it. And I could do the root test, but the ratio test is almost always what we're going to use. We can use root test, but we're almost always going to use ratio test. Okay. So I'm going to take my series, my power series, I'm going to conduct the ratio test on it. That's step one. Step two is when I do my ratio test, just like in kind of my argument before, I'm going to end up with something like this. Okay. I'm going to end up with a limit like this. Okay. And that limit's going to depend on what x is, right? So step two, I want to choose the x's that guarantee that the limit is less than 1. Okay. And then that maybe gives me an interval, right? Centered at A. And then the last step, okay, so I have knowledge right now about everything in that interval. Last step is to test the endpoints. So maybe these steps don't make any sense right now. So let's work through an example and see these steps in action. So maybe I'm given this power series, and I believe this is an example from the book. And the question is, or maybe they say test, or maybe the question is determined, is stated as determine interval and radius of convergence. So maybe that's how my problem's stated. So let's just look at what our steps are. All right, so even if you don't understand them. Step one, take the series and conduct the ratio test. All right, so let's start with that. I'm giving myself some more room. All right, so I conduct the ratio test. So first thing I need to find is an plus 1 over an. Okay. All right, so let's find our an plus 1 first. That would be x minus 3 to the power n plus 1 over n plus 1. And now I need to divide by an, which means multiplying by the reciprocal, right? Okay, let's go ahead and simplify. All right, so this is my an plus 1 over an. Now, that's step one, right? And really, I should be taking the limit of all this, right? Okay, so this is step one. I get this limit here. And x is unknown at this point, okay? But step two is I want to choose x's. So limit is less than 1. Okay, so I want this limit to be less than 1. Let's make a copy of this real quick. Boom. Okay, so I got this thing and I want it to be less than 1, right? Well, let's think about this piece by piece. What's the limit of this piece right here? N over n plus 1. Well, that limit is 1. So if I want to make sure that this overall thing is less than 1, I need to play with this. Okay, so what can I do to guarantee, what can I do with my x's to guarantee the limit of this overall thing is less than 1? I want 1 times x minus 3, the absolute value of that to be less than 1, right? All right, the 1 doesn't make a difference. I can forget about that 1, right? So really what I want is absolute value of x minus 3 to be less than 1. Now the rest is just solving this absolute value inequality. Okay. So review how to deal with these absolute value inequalities. How can I solve this? Well, first thing I can do is drop the absolute value bars and slap a -1 on the other side. So I know this is equivalent to this. And now I want to try and get x by itself, right? So how can I get x by itself? I'm going to add 3 to all 3 sections of this inequality. And I get what? 2 is less than x is less than 4. Okay. And this describes my interval of convergence, right? I got x is less than 2 is less than 4. As long as x is in this interval, this limit is going to be less than 1, and my power series will be absolutely convergent. So I know my power series is going to be convergent between 2 and 4. And notice that that number 3 is right smack dab in the middle, okay? And then if we go back up to our power series, right? Maybe it's not obvious that this is a power series, right? But I could rewrite this thing like that. And now this is my Cn, and this is my x minus a to the power n, okay? So note that that 3 is that center, right? And we see when we look at our interval of convergence, okay, that center is in fact in the center. Okay. Now what's step 3, right? I know my series is convergent everywhere in here, but I don't know what's going on with the endpoints. Okay. So how do I figure out what's going on with the endpoints? Well, my previous theorem doesn't tell me anything about the endpoints. What am I going to do? I'm just going to take my endpoints 2 and 4, and I'm going to plug them in to my original series. Okay, so my original series was this, right? Let's take 2 and plug it into our series. When I plug in 2, what do I get? Okay, I get 2 minus 3 to the power n over n. What is that? Well, that's -1 to the power n over n. Now I ask myself, does this series converge or diverge? Okay. This is the alternating harmonic series. It converges by alternating series test. Okay. So when I plug in that endpoint x equals 2, my series converges. So I want to include that 2 in my interval of convergence. Now let's test 4, x equals 4. When I plug in x equals 4, what happens? Okay, I plug that into my original series and I get what? 4 minus 3 to the power n over n. I simplify, and that's 1 to the power n over n. Well, 1 to the power n is always n, right? Or excuse me, is always 1. So really what I have is just 1 over n. Does this series converge or diverge? It diverges, right? It's the harmonic series, our most famous divergent series. Okay, so that means I don't want to include that endpoint 4. Okay, so my interval of convergence is this thing. From 2 to 4, including 2 and not including 4. So my interval of convergence is 2 comma 4, bracket on the 2, parentheses on the 4. What's the radius of convergence? Well, I'm just going to find the radius of convergence, it's really easy. I'm going to take my interval of convergence. How long is that interval? Well, it's 2 units long, right? I'm going to take that number and divide it by 2, and that gives me my radius, okay? The other way to think about it is, okay, you have your interval, it's centered at 3, it goes out to 2, it goes out to 4, okay? What's, you can think about this as the diameter, and this is the radius, okay? So what is that distance, that radius? Well, it's 1, right? So my radius of convergence is 1. Let's see another example. This is from the exercises in the textbook. So I have -1 to the power n times 4 to the n over square root of n, x to the n. Okay, so let's dissect this. Is this a power series? Well, yeah. I'm going to call all this stuff on the left, that's my Cn. And then what's that x to the n? Well, that's really just x minus 0 to the power n, right? So I have a power series centered at 0, and these are my Cn's. Okay. Let's try ratio test. So again, I want to find an plus 1 over an. Okay. Simplify. Okay. Since I'm doing absolute value is going to just obliterate this -1, right? So I can forget about that -1. So really what I have is this. 4 times x times square root of n over square root of n plus 1. And really, I'm considering the limit of everything, right? For a ratio test. Okay. So this is step 1. Step 2, I want to find the x's that make this limit less than 1. So I want 4 times x times, let's see, what's the limit of this thing? The limit of this is 1, right? So I want this to be less than 1. In other words, I want 4x less than 1 greater than -1. So x is less than 1/4 and greater than -1/4. Okay, so my interval of convergence is starting to look like this: -1/4, +1/4. Okay, and then I got that 0 in the middle. All right, last step, test my endpoints. I'm going to take -1/4 and plug it into my original series. What was my original series? All right, so I plug in -1/4 to my original series for x. Let's simplify. All right, 4 to the n times -1/4 to the power n. Well, that's going to become 4 times -1/4 to the power n. Well, that simplifies as -1 to the power n. Okay. Now, what's going on here? I got two -1s to the power n. Okay. Well, I could simplify that further. As -1 to the power 2n, right? And really, it doesn't matter what's going on with n. I could also think about that as 2 or n times 2, right? And really, I could first consider -1 to the power n and then square that. That's the same thing. So no matter what this is, what this is, whether it's positive or negative, I'm squaring it. So this thing on top is always going to be positive, right? So really what I have is 1 over square root of n, which is 1 over n to the power 1/2. So this is a p series. P is less than 1, so my series is divergent. Okay. So what was going on? I plugged in -1/4 and saw my series was divergent. So I don't want to include that -1/4. Now let's plug in x equals +1/4 to my series. Simplify. It simplifies as what? -1 to the n over square root of n. This is an alternating series. I use alternating series tests and see it's convergent. So the series is convergent when I plug in +1/4. So that means I want to include that +1/4. And of course, it converges everywhere in between those two values. So I see my interval of convergence is -1/4 with a parentheses to +1/4 with a bracket. What's the radius of convergence? Well, I just take this distance and divide it by 2. Let's see. This interval is 1/2 unit long. I divide by 2 and I get 1/4. And that's all the material for this section, okay? Everything, all your other problems are going to be the exact same methodology, just, different specifics, okay? So if you can follow along these two problems, these couple example problems I did, you should be able to replicate all that. This is, again, I'm going to start doing these problem videos again, because this is material you definitely want to see a lot of examples of. So problem video to come.